welcome to this lecture course on noise control in mechanical systems with me, Professor Sneha Singh, and we have been discussing about micro perforated panel sound absorbers or simply the MPP absorbers, and we studied what is an MPP and what is the sound absorption mechanism behind this, what leads to a much higher absorption. Mechanisms such as the viscous thermal losses or thermoviscous losses, and the resonance that mostly dominate, and then an expression for Z of MPP was obtained and the Z of the cavity behind the MPP. So, today we will see what is the effect of the MPP parameters on the overall acoustic impedance and the absorption coefficient of an MPP, some advantages and limitations we will see, some modifications that can be done to simple single leaf MPP absorbers, what is the effect of porous material. So, effect of MPP parameters. So, this is the equation that we had obtained. So, the Z of MPP is given by this formulation here and the Z of cavity is given by this formulation here. So, let us first see what is the effect of cavity depth. So, first we see that cavity depth appears in this acoustic impedance of the cavity. So, here it depends on the characteristic medium obviously, and given that we are using the micro perforated panel absorbers in the air medium, this thing becomes fixed. So, this is like the air medium. So, it then only depends on the frequency and the depth of the cavity. So, as the depth of the cavity will reduce, the acoustic impedance of the cavity is going to go up. In general, if you observe the behavior of the minus j cot function, and the absorption coefficient is given by this 1 minus mod of z minus 1 by z plus 1 whole square, where z is a summation of these two terms. Now, let us see how the z of MPP varies with the various changes. Okay. This is a very complex expression. So, just deriving and solving the typical frequencies is not possible within the scope of this lecture series. So, we will just see that overall how the various parameters are affecting the impedance. So, let us start with porosity. If you see, in the first case, in the first term the porosity is here in the denominator, nowhere here, x is r into this quantity here, the porosity is nowhere, and then it is again appearing here and nowhere else. So, basically what is happening is that Z of MPP can be written as 1 by sigma times some complex number which is independent of sigma. Or another way of writing this could be that you can simply say Z of sigma minus some factor which is independent of sigma, some constant. Okay. So, as the sigma will reduce, the acoustic impedance is going to go up. That is a simple formulation. Now, let us study what would be the effect of Z on the R. So, for this let us see where R appears. So, here in the first term you can see that x directly depends on R. It is R multiplied by some factor which is independent of R. So, here we will have a term which is root of 1 plus some R square thing, and then we have R and R square here, then we have R square here in denominator, and then what we have is that again an R square from here and here. If you bring it down, what you will see that, let us write some constant terms. So, there are some constant terms and then R square here. So, and then in the first term what we have is 1 plus some R square times of things, and then again some constant term, then R square, and then multiplied by R cube like that. So, here we will get a R square and R cube from this particular place here. If you solve these terms, and in the j part what you will get is that you will get some kind of root, inside the root you have an r square term and then some r here and like that. Okay. So, what you see would be that it's a very complicated relationship with r. It's sort of, you know, it's not a easy function. So, experimentally then what it has been found is that as the r increases and then decreases, so the z of MPP rises. So, there is some optimum value at which you get a maximum sort of MPP, and then with the z increase in the z, the impedance is going to increase and decrease like that. So, there is a very complicated relationship which actually is found only observed experimentally. Now, let us see what happens when thickness is there. So, if you just see what is the effect with thickness, T appears here and over here and over here and over here. So, you will see that the first term is dependent, whatever the first term is, it will be dependent on T. The second term, if you multiply T in the numerator and the denominator, it vanishes. So, this will become independent. So, this will be directly proportional to T, this will be independent of T, this term here again would be, you know, directly proportional to T, and this would be constant with T or independent of T. So, basically you will have a term with T to the power 1 both in the real part and the complex part. So, again as T increases, M will increase. Okay. Now, this is a graph that was just made by myself. So, you know that alpha is given by this value 1 minus mod of z minus 1 by z plus 1 whole square. So, I drew a graph of how alpha changes with a change in the overall impedance. Okay. So, this is the total normal acoustic impedance Z, and alpha is given by 1 minus this thing here. So, I simply drew the graph of this to see how alpha is changing with Z. So, what you observe is that alpha rises suddenly, so with the increase in the Z till Z approaches 1, and post that whenever in the zone where Z is greater than 1, alpha decreases with the acoustic impedance. So, this is the characteristics that is observed when Z is greater than 1. Now, we know that here we are taking this Z as the Z of the absorber by Z naught. Okay. This is the relative normal acoustic impedance. So, in most of the cases our medium is going to be the air medium, and any additional material we are adding is going to have an impedance higher than the air medium. So, in most of the cases Z is actually going to be greater than 1, okay. That is going to be the usual case. We have an air medium, and then in the air medium we are suddenly putting some kind of material which will have an impedance higher than air. So, we usually for most of the cases in noise control engineering operate when the relative specific impedance is greater than 1, and hence in that case the behavior that is observed is that alpha decreases with the increase in the Z in this particular fashion. So, we already saw from the equation that this is how the overall Z is sort of increasing or decreasing with respect to the various control parameters, which are the pore radius, the porosity, the panel thickness and the cavity depth. These are the 4 control parameters which are affecting the acoustic impedance of Z. And in this zone, because alpha decreases with the increase in the Z, so the reverse relationship should be there. So, which means that, see over here, so the reverse relationship should be there because alpha Z is increasing, then alpha should be decreasing. So, if you see here, when porosity was decreasing, because porosity was in the reverse, so Z was increasing, and when thickness was increasing, Z was increasing. So, over here what should happen, because Z increases with the decrease in the porosity, alpha should increase with the increase in the porosity, a direct relationship should be there. In the same way, as Z is increasing, a direct relationship is there between Z and T, and so the opposite relationship should be there. So, as the T decreases, only then the alpha is going to rise up. And then when D decreases, Z is increasing, so when D should increase, alpha should increase. and a complicated relationship it will follow with R, which means that when the radius is decreasing, the alpha is going to rise, but beyond a certain point the alpha is going to decrease, like that, some kind of complicated relationship. So, this is just a gist of roughly how the various control parameters or the of an MPP are affecting the absorption coefficient of the MPP. So, a higher cavity depth, a smaller thickness panel and a higher porosity would definitely be more encouraged to increase the alpha. Okay. So, we know that in general what we see is that as the cavity depth is rising, alpha is rising, but just like in the case of panel absorbers and then the perforated panel absorbers, and similarly there are some typical values where suddenly the absorption will reach a maxima or a minima, which is at d is equal to lambda by 4, we will have maximum absorption. So, d is equal to lambda by 4 and its odd multiples, and d is equal to lambda by 2 and its integral multiples. So, the reason for this is same as what has been discussed in the perforated panel, that why this kind of depth leads to a higher absorption and this leads to a lower magnitude of absorption. So, the depth of cavity affects the magnitude of the absorption not just by this relationship, but also at certain values you will get some maxima and the minima. So, care has to be taken while designing the air cavity depth. What are the advantages? They are thin and light, you have thin kind of sheets followed by just air and a rigid backing. So, they are very light and thin in nature, they are durable, okay, and non-combustible, high temperature wear resistant, given that what kind of material you are making your sheet from. They can be painted to make them as aesthetic, okay, and high absorption most importantly. So, most of the advantages would be the same as the panel absorbers, but there is an additional advantage that the magnitude is now higher. Why? Because now we have an additional mechanism which is the viscous loss, and because of that the magnitude is rising up. Okay. Then one of the major limitation of this is that wide range absorption is difficult, because again it is a resonance phenomenon which dominates, and only at those frequencies we observe sharp peaks, albeit much higher in magnitude, but sharp and narrow peaks we are observing, and hence wide range absorption becomes difficult. Okay. So, how can you do wide range absorption? You can install multiple layers of MPP which can lead to increase in cost, weight and the volume of the overall absorber. So, to overcome some of the limitations of the simple single leaf MPP, which is in order to improve the low frequency absorption response, which is to broaden the absorption response, various modifications have been tried out. In fact, MPP is a very ripe area for research in noise control engineering. As the time is going by, new observations are being made and new kind of designs are being proposed in general as the time is going by. Some of the common modifications suggested is that you either add some kind of absorber filling into the MPP cavity, or you, instead of having one panel, you can have two panels in the MPP absorber, or you can have the cavity with different kind of partitionings and each partitioning having different shapes and different fillings. Okay. So, again for this particular lecture course we will only discuss about MPP which is filled with porous absorber, and these other two would be out of scope. So, let us see what happens when the porous absorber is inserted. So, we have already seen that what happens when we fill the cavity of a sealed panel absorber with porous material. We have also seen what happens when we fill the cavity of a perforated panel absorber with a porous material. Similar effect is observed for an MPP. So, what happens? The porous material is being added. So, you can think of it in mathematical terms that whatever is your Z of the MPP, so the porous material acts as an acoustic resistance. So, whatever was your Z of MPPA with some real part and some imaginary part, now you have added the MPPA with some porous material. So, what will happen? The resistance part or the real part of your acoustic impedance is going to rise up, because this could simply be thought of the R initially plus the R dash due to porous material plus Jx. So, it directly adds the acoustic resistance to the model of the MPP, and hence the real part rises. Now, we know that alpha is 1 minus this is the alpha formulation, and R is given by this. Suppose if Z is much greater than 1, then in that case the R is going to become 1 and alpha is going to reach 0. So, whenever you are sort of adding porous material to increase the damping and to increase the resistance, there has to be a limit, because if you reach a much high, if you add too much porous material which sort of rises the overall resistance of the impedance, the resistance rises, then the overall Z increases, then alpha is going to become 0. So, you have to add the porous material that can improve your absorption response, but remember that you also want to allow the sound waves to enter inside the material. So, the opposition should not be too much. The resistance to the flow due to that porous filling should not be much higher than the characteristic impedance of the incident medium. Okay? Suppose this care you are taking and then you are appropriately selecting some porous material and adding it, what will it do? The same effect it will have, it will widen the absorption frequency range, but that can come at a cost of decrease in the absorption magnitude. So, let us see here, this is your MPP followed by a porous material followed by the rigid wall. This is the electric circuit for this. You have the Z of the porous material and the Z of the MPP, they are now in series. Okay, so what is happening is that, suppose sometimes when you select an optimum porous material, then you can observe an overall rise in the sort of absorption as well. So, in that case, given the appropriate filling is selected, it can lead to a rise in the overall absorption because it is increasing. So, in some ways it is going to increase because there is an additional mechanism that is coming into play. Not only the resonance and the thermoviscous losses, but also you have got the thermoviscous losses within the porous material that is adding further to the loss in the sound energy or the sound energy dissipation. So, sometimes this can also be observed, but a lot of care needs to be taken, because if you select the wrong kind of material, and then it can lead to actually a decrease as well. So, here that is why some optimum parameters are given. This is taken from a paper where what they did was, this is the radius of the MPP, the thickness of the panel, the porosity, and the flow resistance of the absorbent is given, which is given as this value, and the cavity depth is this. So, at this particular value they observed that there was a significant rise by adding porous layer, but if this thing increases or decreases, then that rise may not be observed. So, with this we would like to close the lecture on MPP absorbers. Thank you for listening.